All right, good afternoon, everyone. Welcome to our Dig In event for the day. We're gonna wait just a minute or two to let everybody show up, but welcome, glad to have you. Again, welcome everybody. We will give it another minute so that everybody can join, but we're glad to have you.
Okay, we'll get started. Hello, my name is Megan, and I'm the Education and Outreach Chair for WIM in Mining, Arizona. First, we'd like to say welcome and thank you for joining us today for today's talk about the shaft sinking at Resolution Copper. Before getting started, we want to give a brief introduction to our organization and why we're hosting these talks. The Women in Mining Arizona chapter, or WIM Arizona, is a nonprofit organization with several objectives, one of which is to educate our members and the public on technical, economic, regulatory, and other mining-related topics. To meet this commitment, we are hosting these monthly dig-in events. And a brief thank you to our sponsors, the WIM Arizona 2020 Platinum sponsor, Freeport-McMoRan, and the sponsor for today's talk includes Canary Systems as the payload sponsor, and we'll hear from Canary shortly, and Stantec as the prospector sponsor. Thank you very much for making this and our other outreach efforts possible. Now I will turn over to Taylor Don with Canary Systems for a few words from.
Thanks, Megan. Hi, everyone. My name is Taylor Don, and I'm the Mining Group Manager for Canary Systems. And I'd like to thank WIM for giving us the opportunity to speak with you all today. Canary Systems is a market leader in the field of data integration with over 20 years of experience. The company was founded in 1997 by Alex Newer, with the goal of improving safety and risk management through automated monitoring at mines, dams, and civil projects. We have offices located throughout the United States, with our mining group located in Tucson, Arizona, and the company headquarters in New London, New Hampshire. We also have international offices located in Canada, Indonesia, Australia, and Brazil. At Canary Systems, we like to provide our clients with turnkey solutions for their monitoring needs, including instrumentation, automation, hardware solutions, communication systems, and a browser-based user interface to help our clients make data-driven risk management decisions. Our software multi-logger suite is the only tool needed to collect, manage, display, and analyze data for a variety of project types effectively and efficiently. As a vendor-independent platform, ML Suite allows users to seamlessly connect all the links of a monitoring project into a single platform. This approach opens powerful possibilities for cross-referencing any data type, for alarming and notifications based on real-world complexity, for forecasting and recognizing trends, as well as for effective reporting and risk management. ML Suite is capable of presenting at a glance the status of a given project as a whole in a single integrated view within your browser in both 2D and 3D space, with full GIS-enabled mapping support and flexible charting options. If you are interested in more information, please visit us at canarysystems.com. Once again, I would like to thank WIM for giving us this opportunity to speak with you all, and I'm looking forward to today's talk on the shaft sinking at Resolution Copper. Thank you for your time.
Thanks, Taylor. And now I'm going to turn it over to Julia to introduce our speaker.
Thanks, Taylor. Thanks, Megan. Our speaker today is Clarissa Escamilla. She is a geotechnical engineer with Resolution Copper. She's been working in the industry for about 4 years. We're very happy to have her here today. And one of many fun facts about Clarissa is that she has been to both the highest point and the lowest point in the state of Arizona. So thanks, Clarissa. I'll turn it over to you now.
Thanks. Let me share my screen here. Okay. There we go. So, like Julia said, I'm Clarissa Escamilla. I work at Resolution Copper. Just a few more things about me. I love adventures. I love being outside. This picture of me and my husband in Iceland. I love rocks and I love mining, so it's a perfect fit, this job. And I'm actually 6 months pregnant right now, so that'll be really interesting coming up here. So I'm going to be talking about Resolution. It's about 70 miles east of Phoenix. It's one of the largest undeveloped copper deposits. Has potential to supply about a quarter of the US copper needs. It's a porphyry deposit. If you look at the bottom middle picture there, that's what a typical porphyry looks like. It has that bell type shape and different grade shells. And on the right, that's what it looks like at Resolution. The top's been cut off, it's been faulted and dropped, so it's pretty deep. So in porphyries, the mineralization occurs in the wall rocks. And we have indicated and inferred resources of about 1,900 million short tons. Average copper grade is around 1.5% copper. And it puts it up there with Bingham and Grasberg and some of the bigger mines. So last year we were working on deepening 9 shaft. It was originally built to about 4,800 feet below the surface. And our project was to increase it a further 2,000 feet and connect it to 10 shaft. The excavated diameter was about 24 feet, and we finished deepening it in October. We got it to about 6,700 feet. We supported the shaft with shotcrete and concrete, and I'll talk about that here in a second. Some of the interesting facts about the project, about 800 blue wells worth of rock were removed just to do those extra 2,000 feet. We installed 11,000 rock bolts. It's about 6,800 feet deep, which is 23 football field lengths, just to put it in perspective. We used about 500,000 pounds of steel, which is 3 times as heavy as the space shuttle. So a shaft is a vertical opening, provides access to underground mines. They're used to send people, materials underground, bring ore out, and to provide ventilation and utilities. So the purpose for deepening 9 shaft for us was to increase the ventilation and to provide a secondary escapeway to increase safety. So this is your typical shaft sinking cycle. On the far left, it starts with drilling. You drill out a round, and our rounds were about 10 feet. You blast it. Then you muck it out. You scoop all the rock out, put it in a bucket and hoist it up. And then you install your ground support. And then you lower your permanent support, which is your concrete liner. And then you clean off the bench and scale it, make sure everything's good before you start over again. So when you're supporting grounds in the shaft, traditionally you use a bolts and mesh. On the picture on the left, you can see the mesh conduct with some split set bolts there. At Resolution, we were using shotcrete and doing a boltless advance. So what we do is we blast, clear out the muck, spray the round with shotcrete, and then lower the permanent liner. And we could use the shotcrete as a temporary support before lowering the permanent liner for about anywhere between 36 and 72 hours before it had to be lowered. So in a shaft sinking cycle, most of the time gets taken up by mucking. It takes about 35% of your time. Then drilling, which is about a quarter of the time. That's followed by installing your concrete liner. And then shotcreting and services and blasting take about 8% each. And then we didn't really spend much time on bolting with this method because it was all just shotcrete. We did have a few places where we bolted where it was raveling or where the shotcrete just wasn't going to work. But for the most part, it was mainly shotcrete. So there's a few risks with doing this method. The distance between the permanent concrete liner and the shaft bottom is really important. The greater the distance, the higher the risk for failure is because it's your permanent support and what's going to hold your shaft open. But the closer the liner is to your advance, it risks damaging that liner and cracking it, which can also be dangerous. So the liner has to be kept as close as possible, but still far enough away that it's not damaged. So for us, this was about 3 rounds worth, 30 to 40 feet. Using shotcrete over bolts. Some of the good things about this was faster ground support cycle time. It was about 30% faster. It costs less than traditional support because you just spraying shotcrete. It also acted like a skin and lowered the heat in the shaft. And there was less exposure to ground hazards for personnel working on the bench in the shaft because there's less cycle time and less incidents related to ground support occurred. So some of the cons, respirators are required during shotcreting, and there is a small safety hazard because you're working with stored energy, you're spraying the shotcrete out of a hose. And it did leave less time for mapping the face. With bolts and mesh, you can kind of look back up and see past the mesh and see what's there, but shotcrete completely covers it. So you got your one chance to see the face, and that's it. So to make sure that this was progressing safely, we did a lot of QA/QC. On the picture, there is a picture of our 3D scanner. It was very important for all our reporting. We took 3D point scans and we did face mapping for Q and RMR values. We also did wedge analyses to make sure that shotcrete was still the right method for each round. And then we also did a shotcrete QA/QC to make sure our shotcrete thickness was adequate. So this is a picture of our 3D point scan. That's a picture on the right of the actual scan. And once you load it into the computer, you can spin it around, zoom in and out, and look at it. And what we would do is we'd compare the scan to the design, and we could tell how far out of design we were, if we were overbraking or underbraking, and correct it before it became a problem. So we also did some face mapping. Before they shotcreted each round, they'd muck out the rock and then send us down to look at the structures, and we'd record the structures and their orientations to get a Q value, and that would tell us, we'd use that for determining if there were wedges or if this was still like the right method to use. And with the scanning, it also allowed us to get actual true thickness of fault, which was really nice and helpful for geologic modeling, because we were able to load up all the scans in a line and tell exactly where the faults were, what orientations they were, how thick they were, and where they're dipping. So we also did wedge analysis, which I mentioned before with the face mapping. So we'd record the structures, and any that were intersecting, we'd look at the factor of safety and determine if the shotcrete was thick enough to be able to hold that wedge in place before we poured the liner, or if we need to do something else like bolting. And then with each scan that we took, the scanner was able to pick up the previous rounds as well. And since we left about 3 rounds open at a time, we could load them up and see how the shotcrete thickness was looking, and any areas that weren't thick enough, they'd go back and respray before pouring the liner, the permanent liner. So part of deepening the 9 shaft was breaking through into our TPL2 lateral development to connect with 10 shaft. So we had a Tasca do a model for us, and the model indicated that the interaction between the shaft and the lateral development would start about 40 to 50 feet away. And the crown pillar, which is the amount of rock between the shaft and the lateral development, when it was only 40 feet thick, it indicated that there'd only be damaged and distressed ground left. So in order to prevent a caving type failure, we installed a lot of ground support in the lateral development, and we backfilled in that area to prevent the caving failure. And then in the walls and the roof of the intersection, it indicated that the depth of significantly damaged rock would be about 13 to 16 feet deep. And that's about what we saw in our probe holes as well. So breaking through into the lateral development, before the shaft reached 50 feet within the lateral development, we just proceeded as normal. And then once the shaft was less than 50 feet from TPL2, we moved into our phase 2, which was where we piled the muck underneath the area where the shaft was going to break through. And then we monitored for ground deformation and sent out daily reports. And we decided that if we encountered poor rock in those 50 feet, we'd reduce the round length and pour the liner closer. And then one of the other things we also did was the resin injections into the corners of the intersection to strengthen the rock. So we installed a lot of monitoring systems to make sure everything went well. In the top right is a picture of a MPBX, which is an extensometer. And they measured the deformation in the rock, the extension. We also used blast vibration sensors to make sure we weren't aggravating any joints or faults. We had fog lights, which stands for fall of ground. And the way those worked were, if the rock moved more than a certain amount, it would turn red and everyone would know not to go into that area. We didn't have any problems with that though. They all stayed green the whole time. And then we also installed geophones for looking at seismic events. But our geophones, we weren't able to get them calibrated before breaking through. So we were able to tell if we were having seismic events, just not where. And then the monitoring plan was essential, to make sure that the deformation didn't exceed the ground support. The blast vibration monitoring was really interesting to look at. We didn't notice anything weird going on with any joints or anything slipping. And then the laser scanning of each round didn't indicate any problems. And we did a bunch of damage mapping and took photographs of the lateral development area just to make sure we could compare afterwards to make sure there wasn't any damage. And then we did a lot with the displacement monitoring and analysis as well. So this is the area where we put the muck underneath the area where the shaft was going to break through. We were a little short on muck, so we ended up building this wall around it and filled it with foam just to kind of cushion it so it wouldn't damage the level when it broke through. So when you're building a station, usually you want to cut the corners off because the stress concentrates there and they'll fall off. Since we were breaking into a station, we decided our last round was going to be a 20-foot round because we didn't want anyone walking on a 10-foot bench of distressed ground. And we didn't cut the corners because we weren't able to with the drills that far away. But it turned out really well because the ground was actually really high quality. So this is a video of breaking through into the area. The breakthrough area is behind that bulkhead. We weren't able to get a camera closer. But if you watch, nothing in the level moves. It's really neat. It's great. The air rushing through is when the muck fell down. And nothing even shook. There wasn't any damage that we noted. And overall, we were able to complete it safely, which I think was a really big thing. So this is installing the ground support after the muck's broken through, after the round's broken through. The picture on the bottom left there is the muck kind of spilled into the other drifts. So we installed some cable bolts and some grouted dowels above, and then since the corners are really sharp, we wrapped them with straps just to provide enough support so it stays stable. Is there any questions?
This is great. Thank you, Clarissa. We actually do have some questions that have come in the chat and the question and answer. First off is, what was the diameter of the shaft?
The excavated diameter is about 24 feet and the finished diameter is about 22.
How much water was encountered?
That's a good question. There was quite a bit of water. I'd have to double check that, to be honest, though.
Not a problem, but water was encountered. Okay.
Yep.
Was the sinking through the Pinal schist?
Not that I'm aware of. It was mostly, I started at Resolution about a year ago, and they had already started the deepening. We went through some Paleozoic sediments and diabase.
How did you get into this field? What led you to this?
So I started out in geology, doing ore control, and it was fun, but I really like the engineering side of things, and especially breaking things, breaking rocks. It's just been something that I find is fun, I guess.
That's great. I am quite intrigued by how many questions we're getting. Just so everyone knows, we'll try and get through some of these questions. We probably won't be able to get through all of them, but we'll work with Clarissa to hopefully reach back out to you that didn't get questions answered if we get there. Were there any challenges with the LiDAR scanning? And are you planning to continue LiDAR-based monitoring of the shaft and horizontal developments in the future?
Yeah, so some of the challenges that we encountered with the LiDAR scanning, we had the water that we did encounter was very hot, so it created a lot of steam and humidity. And the scanner, it's like a person, it can't see through the humidity. So it wasn't able to always pick up every single detail. And we had to filter through the scans pretty heavily. And that was one of the challenges that we faced. And then we do plan on considering using the scanner for future monitoring as well.
Another one that I thought was quite cute is, can you give us a better term of wedge analysis for those who are not geocentric to start with?
Yeah, so when you go down and you're looking at the rock face, you can see all the fractures and the different ways they go into the rock. So what we do is we measure the strike and dip, which is whether it's going north, south, east, or west. And then the dip is how far it's tilted. And then we put all the orientations together and see if they intersect. And if they intersect, they can pop out of the wall. They'll just slide out. So what we did was we look at those areas where they could slide out and figure out if the shotcrete was enough to hold it in place, or if we need to put a bolt through it to hold it.
Thank you. Here's another one. What is the most critical or nerve-wracking part of sinking the shaft?
I think the most critical part, the part most people are nervous about was actually breaking through into the station, the lateral development. There's always concerns. You're like, oh, what if we're further off than we thought we were? Or what if we didn't put enough ground support? The area would collapse, or things like that. And you start second guessing yourself. But we were really careful about it, and we decided to go very conservative with our approach. And we installed a lot of support underneath in the intersection in that area to make sure it held up. And so that's why in the video, nothing moved at all. It didn't even shake.
What type of explosives were used?
So I believe we used, I want to say ANFO and Emotion, but that might be wrong. I wasn't on the explosive side of things.
That's, you know, we all like blowing stuff up. That's,
yeah.
What was the thickness of the shotcrete layer on average?
So we aimed for a thickness of 3 inches. And then when we did the comparison of the thickness, if it was less than 2, we'd have them go back and respray.
Did you guys need to modify the shotcrete mix as you changed levels in the shaft sinking?
I don't believe so. We did test it in each round to make sure it was still holding up. We did, it's called beam testing, where you spray a few shotcrete beams and then you put a lot of pressure and see how much pressure it takes before it breaks. And if it didn't meet a certain pressure, we'd record it, and then we'd have to go back and look at why and figure out why and make sure that didn't happen again.
And how about we finish with this one for now? Did the shaft stay straight as it was sunk?
Yeah, so that's where the LiDAR scanner helped a lot. We were able to tell if we were deviating, or if there were areas where it was underbroken. They could go in and kind of chip away a little bit to make it back on track. And then we also did a lot of surveying to make sure it was straight.
Thank you so much. Just so everyone knows, we have a ton of questions. This was a great presentation. We had almost 120 people in here today, so we've got lots of questions. We'll work with Clarissa to hopefully answer those questions and get back with you after the presentation. I want to give a heartfelt thank to Clarissa for presenting today on the shaft sinking project at Resolution. As the program's chair for Women in Arizona chapter, I want to invite you to join us for future events. We'll be popping up a screen here in just a second where we have how you can connect with us. This is also going into the chat. You can go ahead and connect with us on different social media platforms. You can become a member, and we have future events as well. We have more dig-ins planned out through the rest of the year. The next couple that we have planned are virtual geology, the history of women mining in Arizona, and high-resolution drone use. So thank you again, Clarissa, and everyone who joined us today for this Women in Mining presentation and dig-in, and I hope you have a great day.